So this question is relatively similar to the last question that we just practiced. The only difference though is the starting product that we're using. The reactions will still be NaBH4 in CH3OH and lithium aluminium hydride in E2O. So let's get this started.
So first we are given 2-bromo 2-methyl propane. If it consider the first case where you are using sodium borohydride in presence of methanol. First, as I told you, it proceeds via SN1 mechanism. So in the SN1, first CBr bonds cleaves and you will get carbocation. Unlike the previous reaction, this proceeds because you have 3 methyl groups attached to this carbon atom, and this is stabilized by 9 hyperconjugations from each from 1 hydrogen bond. So the product is now sodium borohydride will supply hydrogen ion, hydride ions, and you will get H as the product. Now let's come to the second case.
So we get isobutane as the product.
That's Yes, isobutane.
Alright. So what's the next way to solve this?
So in the second case, the same compound you are treating with lithium aluminium hydride. Now if you just write down the product as H, you are wrong, because as I told you, this proceeds via SN2 mechanism. If you remember the mechanism of it, H- attacks on the back side and CBr bonds cleaves from the front side. Now if you see, there are 3 methyl groups attached to this carbon atoms. So this hinders the approach of this hydride ion. As a result, instead of SN2, E2 is more favored.
Okay, so
I mean
as
to
a
say that
consequence of it,
since hydride ion cannot approach from this side, what it do is it will take H plus from this side and CBr bond leaves, and you will get an alkene.
alright. So as you can see from this question, we've realized that via the SN1 mechanism with the C and the Br bond breaking, we do get the expected product. But because of steric hindrance, which is a particular case for this particular compound, we are unable to go through with the SN2 mechanism, and what happens as a consequence is we go through the E2 mechanism, resulting in an alkene. So be careful whenever a question has any form of steric hindrance possible in the compound, and try and draw its structure out and try and visualize it before you go ahead and solve the problem. So now that we're done with this, let's move on to the next question. Let us find the product upon electrolysis of the following compounds.
These reactions comes under method of coal-based electrolysis. If you remember our rule of thumb, which is HELP, gives you a free radical intermediate, where E is electricity. So we can say that in this reaction a free radical intermediate is formed. Now let's see how it forms. First, during electrolysis, if you remember, cation and anion splits and they move toward their respective electrodes. Now you'll get 2K plus cations which move towards cathode, and you'll get an anion, dicarboxylate anion it is. Now at anode, what happens is this loses electrons and you'll get radical, biradical it is. since there are two radicals on the same compound. So now here, since CO2 is more stable, what happens is this bond will undergo homolytic cleavage and you will get CO2 and a biradical as shown. Now
the reason this happens is because CO2 is a very, very stable compound,
yes,
and a lot of energy is released when
yes,
CO2 is formed, so it tends to go this way. Now, what is the next step that can happen? We can either have CH2, the two CH2s attack another pair of CH2s and form a four-membered ring. Is that possible, Gopi?
No, that is not possible, because if you remember, the carbon atom in that compound is, say, it is sp3 hybridized, and the bond angle should be 109 degrees, 28 minutes. But if you see here, the bond angle is 90 degrees. As a result of it, there is a lot of angle strain, so this compound won't form.
Okay, so what is the alternative to it if we will not have a cyclobutane?
Now, the thing is, intermediates are unstable, but
Okay.
two free radicals on the same molecule are very unstable.
Definitely.
So what happens here is, this bond cleaves away and this bond cleaves away. You will get an alkene product.
Okay, interesting. So instead of getting a cyclo product, we get an alkene product as such.
Yes.
Alright, let's look at the second case where the chain is longer, and let's try and see what happens in that particular case. Let's solve the second bit of the question now.
In the second part, the biradical which we get is, now it's very simple that two free radicals on the same molecule is very unstable, and also pentane or hexane rings are highly stable because there is not much angle strain in them, and for this hexane it will arrange in chair form or boat form to reduce the angle strain. As a result of it, they are very much stable, so you will get a pentane ring for the B case.
Okay, so as you can see in this case, we will not have alkene formation as such, but we'll have a cyclopentane.
Yes.
So tell me this, what would happen if this ring becomes even larger?
The thing is, if this becomes even larger, for larger atoms, this cyclic formation is very unstable because angle strain would become more. So what is possible is, it undergoes polymerization. If you take large molecules, then instead of forming the rings, it will undergo polymerization. You will get a polymer.
Okay, so that is a possibility that can also come about if the chains are too long. Alright, so we've now learned, as you can see, that based on the length of the chain, the end product can be entirely different in coal-based electrolysis. So you should always keep in mind as to how long is the chain that is being formed as such. Now that we know that cyclobutane will not be formed because of angle strain, what is the other alternative that's left to us?
If you look at it, you will have two free radicals on the same compound.
And it's very unstable as a result, right?
Yeah. So these two overlap and you will get ethene.
Oh, and that's fairly straightforward. Now we have to find P in the following reaction, where the starting reactant with us is 2-bromo-2-methyl-propane.
Yes.
And we are going to be performing electrolysis on it to get the compound P. So Gopi, tell us how are we going to go about this?
So for this compound we are supplying electricity. So from our thumb rule help, you can say that free radical intermediate is formed here.
Okay. So now we know that a free radical is going to be formed.
Yeah. free radical is formed.
Okay.
So
Will this free radical associate with another free radical and form a bond?
if that is the case, but that's not the case, because these three are very bulky groups and this approach is not favored.
Okay, so because there's going to be a lot of steric hindrance.
Yeah.
Okay, alright. So, what is something else that can happen?
This is not possible.
Okay.
But so the only case which is possible here is elimination reaction,
Okay.
where you cleave the CH bond homolytically and you will get a biradical, and thereby you have an alkene.
Okay, so this is going to result in the formation of an alkene.
Yes.
And so is this going to be a 100% product, or will there be other side products that will be formed as
This
well?
is the 100%.
Okay. So students, remember, in such cases of high steric hindrance, we will not have the two of the
Coupling
of
free
the free radicals as such, but we will in fact end up having an elimination reaction. Now the thing is, as a thought process, what would happen if, as opposed to having 3 methyl groups, we only had 2 methyl groups as such?
If you have 2 methyl groups, then what happens is you will get a free radical here. Now there won't be much steric hindrance for this compound,
Okay.
so you will get this compound.
So will this be a 100% product, or will we also have an elimination reaction with it?
There will also be an elimination product.
Okay, so there will also be an elimination product. And what will the elimination product look like?
Since this is a free radical we have, you will get a biradical like this,
Okay.
and you will get this compound.
Okay. So as you can see, students, in a particularly sterically hindered case, we get 100% compound. But if it's not an absolutely sterically hindered case, there is a possibility of a biradical
Coupling.
of a coupling, and also of an elimination reaction happening.
But here, coupling is the major product, because elimination requires a cleavage of bond.
Okay. So a small percentage of elimination will happen, but
Yeah.
very little as such. So students, you can also gauge the tone of the question by the product, because here it was given to you that only P is being formed. If they had written P plus Q, you would have been able to identify what would the other product be. Obviously in this case there would be no Q, but if say one of these hydrogen were to be removed, you would know that the other product that is going to be formed, say the P plus Q, is going to be the sterically hindered, is going to be the coupled product as such. A very straightforward question: predict A and B in the reactions of the following Grignard. So let's get to it.
So, Grignard, basically RMgX, it provides R minus. The first thing is, it can act as either base or nucleophile. Now, if there is an acidic hydrogen, then it acts as base. If there isn't any acidic hydrogen, then it acts as nucleophile. Now, if there are both acidic hydrogen and an electrophile, then it mostly acts as base, because acid-base reactions are very faster. Now,
Okay.
in this case, for the first compound we have CD3OH. Locate the acidic hydrogen here. If you look at its structure, you'll have CDDOH. Now, this is going to be your acidic hydrogen.
Exactly.
So what happens is, here you have R is equal to CH3. You'll slightly get CH4.
Okay, that's very straightforward. Now what about the other case?
Now consider the next case, where you have CH3OD. Now here the acidic hydrogen is a deuterium atom, and you will get CH3D.
Okay, alright. So these are the two questions, these are the two bits of the question, and you can see how the acidic hydrogen is the one that's picked up by the R part of Grignard's reagent.
Yeah.
Otherwise, if you aren't able to identify what particular hydrogen or what particular monovalent compound is going to be picked up, you might end up getting this wrong.
Now, I want to tell you a few things about this Grignard reagent. Now, first I want to say how this Grignard reagent is formed. You'll start up with an alkyl halide, you treat it with magnesium, you will get RNGX. Now, I want to tell you which hydrogens this Grignard accepts. Now, this Grignard accepts the hydrogens like Grignard accepts this hydrogen, OH, NH, SH, or acid, COOH. Now, I want you to memorize these things because these values are based on the pKa values of this. I mean, the extent to which these release H plus ions. Now,
Okay.
Grignard doesn't accept hydrogen in these molecules, like alkene, say,
Okay.
or alpha hydrogen of the carbonyl compound.
Okay.
This is acidic, but it's not much acidic for Grignard to accept this hydrogen.
Okay.
Also, it won't accept the alpha hydrogen for ether compounds.
Okay, so it doesn't accept it for ethers, it does not accept it for
Alpha hydrogen of the carbonyl compounds.
Okay, and
For alkene.
For an alkene either. But it does accept it for an alkyne.
OH, NH, SH, or carboxylic acid like COOH, and for this compound also. It's a pentane ring with 2 double bonds.
Okay, and the reason, as you can figure out by now, is if the hydrogen atom is removed from there, the stabilization that will happen consequently does not happen on the right side of the page, while it does happen on the left side of the page. Because if you remove a hydrogen atom from the ring, you will notice that it goes into resonance and there are multiple resonating structures that are formed. We already know that SH, NH, OH and COOH are quite adept at handling a negative charge very easily. But the same does not happen with a C double bond or an ether either. So now that you know what are the hydrogens that the Grignard's reagent accepts, you can go ahead and solve any of these problems, and let's move on to the next question.